So, hello. Now I'm also starting to record this exercise, and we are just going through the individual exercises, let's say in a similar sequence like we had it in the lecture. And in this exercise, I would still stay with reactive transfer molding and reactive transfer molded packages. We know the process of reactive transfer molding. It means we have an injection molding machine where we inject the material into the mold. Here it becomes liquid due to heat, and it starts to react. And there are several conditions which must be met in order to have high quality. One of the prerequisites is that the liquid material will be able to reach the end of the mold so that all lead frames are covered. Another thing is, if it would react too fast, it would harden before the last package has been reached, and also the viscosity of that molding compound would be too high, and that would shear off the bonding wires. On the other hand, doing it too slow, for instance by low temperature, would mean that the time of that process is too long. And so if you are able to have the optimum and minimum molding time, you have the optimum process, both with respect to quality and with respect to costs. Okay, but now the very important thing is the reaction. And the chemical reaction, so we have the monomers of the epoxy, and these react also using a hardener. And when we look at the reaction over time, so here we could say that is log of time, we can define a degree of reaction. So a reaction typically cannot be more than 100%, or x is 1, so let's say 100%. And here we have, let's say, the times 10 and so on. And here we can say a typical reaction goes that way. It starts a little slower, and it goes up, and in the end it almost reaches 100%. On the other hand, how can we affect this hardening reaction? So here in that case, we could say, okay, we can perform it at a lower temperature. Then we would have, for instance, cold is blue. This behavior, or we could do it at a higher temperature. So that would be red. And in that way, we approach almost 100%. In reality, it cannot react 100%. Always some molecules will be trapped. So that is a so-called sigmoidal function. And so if we describe x as a function of temperature, no, as a function of time, how would such a formula be? For instance, it could be the x over time is 1 minus e to the power of t divided by tau. Tau is a time constant. And in that way, we could describe such a S-shaped function. Okay, that's a very important function because almost all processes we have in chemistry go into saturation, and here in that way we can describe a saturation at 100%. Okay, now the question is, here we had the different temperatures. So we had T3, which is larger than T2, which is larger than T1. My question to you is, which formula can we use in order to describe reaction rate for a chemical reaction? So that's time. And now I would like to know the temperature. So, give me an idea. Can you respond to me? Yes. Some factors of the Ki1 and Ki2. Okay. Yeah, that's in the lecture notes. That formula is even a little more complex, but the typical standard formula for temperature dependency, for instance, a rate if you have some rate, so per time. How do we call such a formula? It's a well-known name, named after a professor from Sweden in the 19th century. He was famous at chemistry and chemical physics. So, do you know his name? He has a Latin name. His name was Arrhenius. And do you know the formula now? It's an Arrhenius formula. And it says it's x0 times e to the power of minus activation energy divided by kT, and how do we measure temperature? We measure it in Kelvin. We can also write x0 times e to the power of minus q divided by RT. So in that case, that's how the chemists and the engineers normally write it. It's R is the gas constant in joule per mole and Kelvin, and here that's the physics version. Here we have the Boltzmann constant and the activation energy in electron volt. Okay. I hope you all heard about this formula previously, because it's very important in engineering. Okay. Now, as the time constant is proportional to the inverse of the x, we can say the time constant, it becomes shorter with higher temperature, so it is the time constant is tau 0 times e to the power of minus EA divided by kT. So typically, let's say activation energies are in the order of magnitude of electron volts. so a few electron volts. The Boltzmann constant you will find at Wikipedia or elsewhere. Okay, what is the time constant? What's the meaning of the time constant? The time constant is where most of the reaction has taken place. So the time constant is typically at 63%. If x is 63%, then we have the time constant. You can find it, put t and tau equal, and then you get precisely 63.2 for the x of t. So that's a reaction, and that's the time dependency, how a molding compound is hardening over time and as a function of temperature. And normally that question is on the border of assembly and packaging. On the other hand, as I know, many of you don't know about such behavior, but it's very important in engineering to know about such description, both for time and also for temperature dependency. That's the reason why I integrated this into my lecture. So the next question would be, oh yes, now something. Yeah, please.
On the time dependent, I think it should we have the minus exponential of minus t divided by time constant?
Where? On the tau. Yeah. You are absolutely correct. Sometimes I'm a little too sloppy, I must admit. So it's always good to have a critical look at that, what I write and hear. So that was your remark, yes? Okay. Exercise 11. So some are here. List 2 examples of such reactions in the field of assembly and packaging. Generally, one example is the hardening of resins. And here we must say it's molding compounds, adhesives, sinter pastes, so normally you can be fast having such a reaction, let's say to a high degree, maybe 90 degree, but the last few percent of the reaction takes always long to accomplish this. So the second is saturation of a package with water. So we have that package. And the water goes in, so it's a similar dependency. The next question is quite hard to accomplish. Many problems we find in packaging have to do with stress. And the question is how stress will develop. And maybe I just go to the previous slide. So we have that pre-assembly, and that is put into the molding machine. And typically we have some, maybe I make it a little larger, we have some assembly in a multilayer, and it consists from the top of a molding compound of a silicon, of a copper, and again of the molding compound. And now let's assume we take only a portion. For instance, we would have just the stack, a molding compound. Now my question is, would you like it against silicon or would you like it against copper? Give me your preference. Go ahead. Okay, so I take the silicon. We would have the silicon between the molding compound. And now that's the silicon, the molding compound. Okay, and we have an initial length L0, and here that's a plane of symmetry, so we start from the middle here. And that is directly after molding. Of course, the materials go further here, but we only model a segment of it. So, what will happen when we cool it? Can you give me a proposal? What will happen when this stack is cooled? Are you there? Hello? Okay, that's very good. So I make a sketch, which is a little different. So we have the cooling, let's say from T mold to T ambient. Yeah? Okay. So the silicon will also shrink a little. But the question is, will it look like this? Do you think so or not? And now give me arguments. After the cooling, would it look like that? No, it will not bend. Okay, go ahead.
If you have good adhesion,
Yeah.
the molding compound on the surface where it touches the silicon will stay, but it will shrink on the top, so there will be a tension in the molding compound. And but in this case, it won't bend because the molding compound is on both sides, so there will be like tension. The most tension will, I think, be in the molding compound itself, and will like create a diagonal.
Yeah. Now I have made, based on your proposal, I have made the blue line, so it will stick, and in the end of that segment will look like this, yeah? In an idealized way. You are right. It is here, for simplification, I made it a symmetric problem, so it will not bend. Would you agree somewhere here in between, the blue line represents the end of our piece of assembly. Do you agree? The lady which just gave me the remark, that's a question to...
Yeah, but I think maybe the corner, the top and bottom corner might go more towards the thing. So it's like a bit like a round shape maybe.
Okay, I agree, but here we just do it in an idealized way, yeah? So what I can do here is just, let's say, the most simple thing. There are lots of publication on that field. For instance, there's a guy from America, Mr. Suhir. He did some famous publications, or Mr. Tsai, he extended the work of Mr. Suhir. So in that way, but here it's just to show you the principle, and so I make it as simple as possible. And it's still complex because we could say there are several conditions which must be met. And one of the conditions is the equilibrium of forces. Furthermore, as you have made the remark, it is coupled in a sufficiently strong way. So we also have, it is a continuous body. So that means, in the end, the length of the molding compound is same like length of the silicon. And the equilibrium of forces says the forces which pull the molding compound are the same or add together with the forces and the silicon to 0. So from the outside it is force free, otherwise it would move, for instance, what it doesn't do. So, yes. What else do we have to know? Now, yes. What do you have an idea? What else is needed? How do we describe thermal expansion? Yes, how do we describe a small formula giving us thermal expansion? What is it?
The change in length with regard divided through the length is the thermal
Okay.
coefficient times temperature.
Times temperature change, yeah? Okay. That is, yeah. And what is the length per length? What kind of property is it? Yes, very good. I must admit, in previous years, often there was no one knowing this, so that's a thermal strain. Please note, and that is important, that thermal strain is not elastic strain. It's some different strain. Only if a system is hindered from building up thermal strains, these strains will develop as elastic strains. Yeah, so you can see it also from the fact that elastic strains are related to stresses with which formula? So, and now here we come to the property which we would like to know. That's the strain, the stress, because that's relevant and that will kill our device if stress is too high. So, how is stress related to strain? Go ahead. Okay, so that's a simple formula. Sigma is E epsilon. So, of course, sigma molding compound is E molding compound times epsilon molding compound. The sigma in the silicon is so here we have 4 unknown, and we must say the following. We must say the following. We have 4 unknown properties. And so we need 4 equations. Okay. But as we have, yes, what do we have? We have here the equilibrium of forces. That's one equation. We have a second equation which gives us the description of the continuous body here. That's a second equation. And the third, then we have this dependency, sigma is equal to E epsilon. And what is still needed is what the initial thermal strain is, and that is epsilon thermal strain is alpha times delta T. And in that way, we have sufficient of equations in order to know what happened here. And so, first of all, yeah, I missed something. Sorry. I think I made a mistake. That should be the blue. I eliminated the contraction of the silicon. And in that way, it should be, of course, here. And now we could say the following. When we look at the thermal strain difference, so that is what we have here. So that's a strain difference. And of course, we can still show the details of that because we know that properties. So that is the delta T. I don't know what's going on here. Times the alpha of the molding compound minus the alpha of the silicon. Okay, so delta epsilon T is known. So that's something we can already have. But the next thing is we must know about the elastic strains. And we can say, when we go back, that is the elastic strain in the molding compound plus the elastic strain in the silicon. That would be the same like the delta epsilon T. So now we have a look. The molding compound is pulled, it has a positive, and the silicon is compressed, so it has a negative. So we must take the difference. So can you still follow? So in that way, we know. In that way, we know what in fact, that describes that it is continuous. That's equivalent to our description. LMC is okay. So what else do we need here? We know this, but we do not know these properties. Now we have to address the forces. The force in the molding compound is how much? Can you give me a guess how much it is? It is the stress in the molding compound times the area of the molding compound. And the area of the molding compound is the thickness of the molding compound multiplied with the width. Okay, let's go back. So if we would we could say that is the width, and that is T, that is T, and that is okay. In that way, we have defined also these properties. So both have same width here when we regard it. What else do we need? The force in the silicon is, what is it? Stress in the silicon area. So, what's the property we are interested in? I just would like to highlight it. Of course, that's the property we are interested in. Stress in silicon, because that will kill our device. Okay. So again, we can modify our formula, and we say sigma molding compound times A molding compound plus sigma silicon times A silicon is 0, or we could also say sigma silicon, no, sigma silicon times thickness of the silicon plus sigma molding compound times thickness of the molding compound is 0. So here we got one formula. Here we got a second formula, which is important. And now what we could say is we could change these strains for stresses. How can we do that? Again, we take this formula, and delta epsilon t is, so sigma is E epsilon, epsilon is sigma divided by E. And in that way, we can modify that formula. The epsilon, delta epsilon t is sigma in the molding compound divided by E of the molding compound minus sigma in the silicon by. Okay. And now here we got, can we solve our problem now? Of course we can. So that's number one. That's number two. And in that way, we can either resolve this for the sigma silicon, and we could. So we have two equations. With two unknown properties, and in that way we can modify the whole formula. So that is known, that is known, that should be known, that should be known, and that should be known. Okay. So sigma silicon Okay. That is delta alpha times delta t. Okay, that's a strain, that's a strain, that's a strain, and this is something like a force normalized to a width. Okay, how shall we resolve this formula? We are interested in the silicon. So what we could say here is the sigma molding compound is minus sigma silicon times so, okay. Now we can say delta epsilon t is sigma silicon times T silicon divided by T molding compound divided by E molding compound minus sigma silicon to E silicon. So delta epsilon T is sigma silicon times okay, and in that way, sigma silicon.
You missed the minus in front of the delta epsilon equals, and then there's a minus in it.
Where is it? Here?
In the third line?
Yeah.
Third line?
Yeah.
Delta epsilon minus, because MC is minus 15.
Here?
No, where you were just before. No. The delta epsilon equals minus, then sigma FE times FE.
Stop it. The line 2 is still okay.
Line 2 is okay.
Delta.
Then you replace the sigma molding compound, and this has a minus in front.
Yeah. Due to this strange line, it, yeah. Yeah, here. We missed it, yeah. Okay, you are right. So, and so here it is a minus, yeah?
Yes, and in the next line as well.
So here it is a plus.
No, the first one.
So.
No.
Here I put a minus. Here that minus is okay. So I put the minus to the other side, and here I say a plus. That's correct.
No.
That minus is okay. That minus is okay. Because here it was.
Okay, you put the minus on the answer.
Yeah, I did. Okay, sigma silicon is minus delta alpha delta T divided by here that is more important. Yes, so we must also regard this formula a little, because in later parts of the lecture we must come back to this. So we have a stress. It's proportional to a strain multiplied with a Young's modulus. Yeah, the inverse of the inverse is again the direct value, and so in that way, generally we could write it that way. Somehow sigma or delta sigma is something like delta alpha, delta t times the effective Young's modulus. And now we can see that that system doesn't react very well. Strange thing. Now this page has vanished. Okay. So we must come back here. So in the end, we can write it in a way, always the thermal stress or stress change is delta alpha times delta T times the effective Young's modulus. And in our case, the E effective was 1 divided by something like T silicon divided by T molding compound times the E of the molding compound plus 1 divided by a silicon. That was what we found out. And in that way, we can say this effective Young's modulus is, as you have seen, it's not very easy to find. In most cases, for instance, as you measure it, as you mentioned, the edges will be rounded a little, or it's no longer rectangular corner we have. That's reality. And due to this, and this real behavior is very hard to compute with analytical formulas, and that's a reason why in most cases we use finite element analysis. So the main reason in such complex mechanical problems we use finite element analysis is more or less we want to know the effective Young's modulus. Also, it must be mentioned that this delta alpha is also temperature dependent. And it is, yes, we have the glass transition, for instance, and also the effective Young's modulus, it's also temperature dependent. Okay, that's how we compute stresses. So more or less, we have some conditions from mechanics. We have the thermal expansion. We have the linear elastic behavior. We have the equilibrium of forces, and we maintain a continuous body. And in that way, we got sufficient information to solve this stress-strain problem. Yeah, go ahead. Please speak louder.
Can you give a quick summary of the previous solution to the question in a brief manner, in a stepwise fashion?
Okay, so yeah, maybe I just write it down, the steps. First of all, describe thermal expansion. So here you get the thermal strain difference, and that's delta alpha, delta T. That's an important property. The second is, what is the dependency between stress and strain? And in our case, it is sigma is E epsilon, and that's the most simple description we have. And now, as we want to know the stress in the silicon, we have to have some information which relates both stresses and strains, and one of these is equilibrium of forces. And that also leads to an equilibrium of stresses. So that's in some way how finite elements also works. It just sums up all strains in all elements, and also that sum of all stresses should be zero, and that's equivalent to the sum of all forces is zero. Okay, and the force is it's a continuous body. So more or less, the length of the molding compound is the length of the silicon, or you can say both length changes which are thermal strains are equivalent to the elastic strains. And in that way, we get enough information. So we first have 4 equations with 4 unknown. And then we get, in the end, we get to 2 equations. So here we eliminate strain. And here we have 2 equations, 2 unknown. And due to this equilibrium of forces, in the end we only have 1 equation for sigma silicon. Okay, and that's the way what the principle is. And here we have seen, let's say, the basic of mechanics of thermal expansion. Again, please note, thermal expansion alone, for instance, in a homogeneous body, will not lead to elastic strain, and it will also not lead to elastic stresses. But there will be stresses and elastic strains. For instance, if we have a homogeneous body which has a temperature distribution, yes? In that case, again, we have delta alpha, delta T. Or, in fact, this should be written in a way, it's T times delta alpha plus alpha times delta T. And in that way, if we would have a homogeneous body, then it would be relevant that we have a homogeneous CTE multiplied with the temperature difference, and again, that gives us a strain difference which acts as an elastic strain. Okay, so we are finished now. Thanks for your attention, and yes, I will upload the next lecture. Goodbye.